Okay, today we're in section 4.3, part A, exponential equations and logarithmic functions. We already know that an exponential function is in the form of f of x equals b to the x. It's also 1 to 1, so we know it does have an inverse. So we're going to find its inverse. We're going to use the example of f of x equals 3 to the x. If you just start plugging in values for x, if you plug in -1, 3 to the negative first power is 1/3. 3 to the 0 is 1. 3 to the first is 3, and 3 squared is 9. Now if we reverse all those in order to be the inverse function, all of the domain values then become the range, and the range becomes the domain. So each of these x and y coordinates reverse. So now the x values are the y values of the original function, and the outputs are going to be the original inputs, or the original domain. So if we plot the original function, we're going to put that in blue. If we have the original points of -1, 1/3, at 0, it's at 1 where it hits the y-axis, 1, 3, it's 3 to the first, and 2, 9 is 3 squared. When you graph this, this is going to be the function where it equals 3 to the x. Now if we flip our attention over to the inverse function, we're going to have every one of these points have the x and the y coordinates reversed. So our coordinate of -1, 1/3 now goes to 1/3, -1. Our point at 0, 1 goes to 1, 0. Our point at 1, 3 goes to 3, 1. And our point from 2, 9 goes to 9, 2. And then we connect those where it used to run along the x-axis and exponentially increase. Now it runs along the y-axis and increases to the right. Now if we look at this function and we solve it the way we normally do with our solving for an inverse, we switch the x and the y, so it was y equals 3 to the x, now it's going to be x equals 3 to the y. That is our new equation. However, we don't have a way to solve this by algebraic operations. So in order to make a solution for that, we can use logarithms. So if you look at this equation where x and b are going to be positive numbers, and then b can't equal 1. Just like in an exponential function, if you had the base of 1, 1 to the x would be a constant function at y equals 1. So the base is still not going to be equal to 1, even when we change it to a logarithm form. So in this log form, b from our exponential equation was the base. It's still the base of our log. And if you raise that to the power of y, and then we make that equal to x, that's what its equivalent is in our exponential function. So you kind of look at that as like a little circle of life or circle of logs. The base of the log is still the base. Raised to the y equals what you're evaluating the log at x. So if we convert back and forth between a log and an exponential, if you do the little circle of life here, base is still the base. It's raised to the power of y, and it equals x. So this would be 3 to the second power is equal to 9. Which I would hope you already know is a true statement. Looking at log base 25 of 5 equals 1/2. 25 is still the base. It's raised to the power of 1/2, and that's equal to what you're evaluating log at of 5. If we go in the opposite direction and we convert from exponential form over to logarithmic form, this base is still the base. That's log base 10. And the two other things are going to flip over the equal sign. Log base 10 of 100 is equal to 2. So you can still do that little circle of life to check it. You would see here that 10 to the second power equals 100 was the original statement. And looking at this last one over here, we have the base of 3. So this is log base 3. These two flip over the equal sign. 1/9 equals -2. And again, if you check this with a little circle of logs, 3 to the negative second power is equal to 1/9.